So last time we have already looked few examples of beta cleavage. So today also we'll see the photochemical beta cleavage of some alicyclic ketones. So few more, few more examples of beta cleavage of alicyclic ketones. So it has been found that if we have a system like this, cyclohexanone with a substituent at alpha carbon O SO2 CH3, this under photolytic condition go beta cleavage. This is alpha bond, this is beta bond cleavage. So give a a radical pair OSO2 CH3. It has also been found that they may also exist as a zootronic species, so this may also exist as a, the positive charge. Here is a dimethyl here. Is another methyl here. Dimethyl here and methyl here. Okay. And then this may have a positive charge and O. So there are quite evidence that the beta cleavage species may also exist as a dipolar species, zootronic species. So this on further reaction undergo 1,2 shift. There is a shift of this one of the methyl group to give a new diradical, this one, and then this may lose minus H dot, or if it is a zootronic species, it will lose, if it is which may lose minus H plus to give so we can see starting from this the cyclohexanone with trimethyl substituent, alpha carbon is substituted with OSO2 CH3 under photolytic condition may undergo beta bond cleavage to give either a diradical species or a zootronic species, may undergo 1,2 shift. So if this species is operating, then we expect methyl group 1,2 shift. To get a positive charge here, and then this will lose minus H plus to give a alpha beta unsaturated. So you can see from a isolated carbonyl we ended up with alpha beta unsaturated with a rearranged methyl group, alpha beta saturated. Here's another example of similar type of beta bond cleavage. Here we have an acetoxy group. So we have a substituent like this. This is another example. We have a C6H5. You have a alpha carbon. This is the carbonyl pH. This is OAC. This is a phenyl group, and this is OCH3. So if we have a system like this, and this is under photolytic condition, also undergo this alpha bond, this is alpha bond, this is beta bond, so it undergo beta bond cleavage, beta bond, beta cleavage to give a acetoxy radical, OCH3. You have a radical here, CHOAC radical. So this is the species which is formed, and then it has been found that this radical incorporates in the cyclization involving the one of the double bond of the benzene ring. So there is a possibility of a attack of this. So we are going to get 1, 2, 3, 4, 5-membered ring with an oxygen containing heterocycle. Right, this is OCH3, and then we have a radical here, pH, and this is get a double bond here. So this will get aromatized very fast. Dihydro derivative is this will aromatize minus H dot, losing molecule of the may combine with this. This will actually it is going to lose minus ACOH, minus acetic acid, by abstracting this. So we are going to get a aromatic, fully aromatic system. The phenyl group is OCH3. So you can see this is this rearrangement. The ketone carbon compounds undergo beta bond cleavage to give, in this case, alpha beta unsaturated system through the migration of phenyl group. In this case, the stoxy group cleaves off, and then the radical generated on the alpha carbon after the beta cleavage involves in the cyclization involving the double bond of benzene ring with the carbonyl to give a 5-membered ring system. So this is a benzofuran derivative, benzofuran. So these reactions have been exploited in synthesizing the synthetically important compounds. So is another example of the photoreaction of alpha halocyclic ketone. Photoreaction of alpha halocyclic ketone. And here if we have a system like this one is a carbonyl here, there is a chloro group, this is alpha halo ketone, alpha halocyclic ketone, alpha halocyclic ketone. So under photolytic condition, as usual, undergo beta cleavage. This is a alpha bond, is a beta bond to give a diradical radical plus Cl minus, and then of course it is in this case it has been found that it has a zeotronic species H, a positive charge here, zeotronic species, and then this has been found to undergo a rearrangement in such a way that goes like this, and then there is a double bond here, is a double bond here, this double bond attacks this. So we end up with a cyclic structure with there's a cleavage of this. This bond gets cleavage, and then there is a formation of cyclopropane. Cleavage of this bond and then formation of cyclopropane here. Formation of cyclopropane. So we get cyclopropane, and then is a carbonyl, there's a double bond here, all right, and then we end up with a positive charge at this carbon. Now this is trapped by methanol, CH3OH minus HCl, loss of Cl minus to give a product like this. So if you write this product in a better way, there is a attack of methanol group, OCH3, and then of course loss of proton. So we end up with so if we write in a better way, it looks like this: C double bond O, OCH3, double bond O, OCH3, with a double bond. So you can see a bicyclic system such as this one, alpha haloketone, under photolytic condition going via beta bond cleavage gives a 3-membered ring. So it's a very nice rearrangement via going by beta bond. So we can see more examples of beta bond cleavage under photolytic condition, which are rearranging to synthetically important products such as this benzofuran here, alpha beta unsaturated carbonyl system, and of course here is a construction of a bicyclic construction of 3-membered ring. So going further, under this, it has been found that the photochemistry of 4,4-disubstituted cyclohexenone, photochemistry of 4,4-disubstituted cyclohexenone, 4,4-disubstituted cyclohexenone. We have already seen this. If we have a system like this under photolytic condition, it undergoes rearrangement to give bicyclic system. First, a 1,2 diradical, since there is a double bond in conjugation, 1,4 diradical, then going to a deuteronic species, and then the shifting of this, the generation of a more stable. So this we already have seen that 4,4-disubstituted cyclohexenone undergo rearrangement to give 1,6 monocyclic 6-membered ring going to 5M3. It's a very nice rearrangement. We have already seen this now. Now what happens in the case of 4,4-disubstituted cyclopentenone? 4,4-disubstituted substituted 4,4-disubstituted cyclopentenone. So if we have instead of 6-membered ring, if we have a 5-membered ring, so what happens? And that's we would like to see in this case. So you have a disubstituted maybe alkyl group under photolytic condition. It goes to a first to a, of course, diradical here, excitation, then there is a double bond, so it will get you have a 1,4 diradical, R. This 1,4 diradical undergo R group, the alkyl transfer. So it gets a species like this. R is R here. Okay, radical. Now this gets cyclized. This can attack here to give a to get a bicyclic ring system. R and R. Now it has been found that this opens up because it's a highly unstable system. 1, 2, 3, 4, 4 and 3 system as a 4 and 3 highly unstable, so opens up to give a ketene derived product. Right. So we can see the in contrast to 4,4 cyclohexenone, the cyclopentenone undergo another interesting rearrangement. First the excitation of the carbonyl, then to a 1,4 diradical, and then the migration 1,2 shift, 1,2 shift to give a new 1,4 diradical, 1,4 diradical, and then the bicyclic system, and then cleavage of this bicyclic system to give a teaching. And this can of course undergo different products, can acid on reacting moisture or an ester on reaction methanol. So this is in contrast to this, we see another interesting rearrangement in the case of cyclosine. Now we have already seen that the carbene is a very good intermediate generated through photochemical system. So generation of carbene can be generated very well by say for example diazomethane, CH2N2, diazomethane. On we can write this by expanding the two nitrogen atom in this CH2 double bond N, it becomes N minus, is a positive, and then this can be written in a much another structure of diazomethane. A dipolar structure can be written CH2 minus N, triple bond N, and so these are structures can be written. Now it has been found that this on photolysis, loses minus loss of nitrogen, generate CH2 radical. This is carbene, ketene, carbene. Now it has been found that when the photolysis was carried out on direct photolysis is a singlet carbene. If the irradiation is carried out in the presence of sensitizer, it also loses minus N2 to give triplet carbene. Plus nitrogen loss. So these investigations had already been well established, and it has been found that the reactivity of singlet carbene and triplet carbines, these two species react in two different ways. For example, the so for example, we have a CR2. This is a this. So this we have a singlet carbene. This is singlet carbene R2. The nature of reactivity of singlet carbene has been found to be zootroinic. Zootroinic. On the other hand, triplet carbene R2 is a triplet. Triplet carbene has been found to be this is deuteronic, and this is diradical. Diradical. So this investigation has already been well established. The singlet carbene is a deuteronic species. Reacts as a reacts as electrophile. Reacts as an electrophile. Whereas the triplet carbene is a diradical species, act in a radical fashion. Reacts in a radical fashion. And this the reactivity has been well established on reaction of these two different carbenes with species like, say for example, if we have a singlet carbene reacts with isopropanol. So if we have a singlet carbene, we have a, say, diphenyl carbene is a singlet. Singlet carbene CH3, CH3, CH3. The singlet carbene react with isopropanol in such a way that this is abstract. The lone pair of, as mentioned, it acts as a nucleophile. So there is an attack of lone pair of this oxygen and OH of the isopropanol to generate a pH COH CH3 CH3H, and then this there is a this will have a positive charge here. This is an isopropanol. This is a negative charge. Is a positive charge. And there is a proton shift. So C H has come already here, and then O CH3 CH3H, and now this is the product, zootroinic product. This is a dipolar species. This is the isolated product. So here's zootroinic. Ionic product. So you can see that the singlet carbene reacts in a fashion in such a way that the lone pair of oxygen isopropanol acts in a electrophilic fashion to give a zootroinic species, which in turn gives this product. On the other hand, the reaction of the triplet carbene with isopropanol reacts in a different way to give different products. The product obtained in the triplet carbene, we have a diphenyl carbene, triplet diphenyl carbene reacts in such a way that is going to extract CH3OH. So this is the radical is going to abstract a hydrogen atom from the isopropanol to give a species like this, H has 2 pH diphenyl. This is the radical here, plus COH, CH3, CH3. So radical pair is formed on reaction of triplet oxygen, and then the isolated product is going to be the CH2. So it gets pH plus ketone. So this is the isolated product. So you can see the singlet and triplet carbene acts in two different ways, and as evident from these two reactions, the singlet carbene on reaction with isopropanol acts as an electrophile by the attack of the lone pair of oxygen of the isopropanol to give a zirconic pair, which in turn gives this ether linkage. On the other hand, the triplet carbene is a radiculoid species, is abstracting hydrogen atom from the isopropanol to give a radical pair, which on further transformation gives these two products as an isolated product. So we stop here, and thank you very much.